Okay, let's take a look at question 9, topic set 6. This question tells us that we have water with some quantity, and initially it starts with volume of 30.6 liter, and then the water condenses from gas to liquid at the same temperature and pressure, and during the condensation you release some heat, and then it's saying what's the delta E if you know the density of water. Okay, so let's think about delta E real quickly, right? So delta E is equal to two components, W plus Q, or work plus heat, right? Now we see here that in the information that we're given in the question, heat is already given directly. So the only quantity we have to calculate then is work in order to be able to solve for delta E. So work, as you remember, is negative P external times delta V, which is the same as V final minus V initial. Okay, so we have to get those two numbers. Now, if you look at the information in the question, we actually know some of these numbers already. Our P external is really just 1 atmosphere. Our volume initial is 30.6 liter. So it's really this that we have to figure out, the final volume. And let's draw out the situation so it makes a little bit more sense. So it says that you start with your water in a volume of 30.6. Now that water originally is in the gas phase. So you can see right here H2O gas. So that means that you just have steam in this container with volume of 30.6 liter. And then what happens is condensation occurs, which means that all the gas gets converted to liquid. And of course, a liquid doesn't occupy as much space as a gas. So as a result, what happens is there's a huge drop in volume. So what we have to figure out is what's the volume of that water in the liquid phase, because that's going to be our final volume that we're going to use in our calculation. They give us density. So if you think about density and trying to calculate volume, remember your density relationship, which means volume is just mass over density. Well, we need mass. We were told that there's 1 mole of this water sample, so that means that we can use our number of moles and molar mass to calculate our mass. So let's do that. So our number of moles is 1. Molar mass of water is 18. The density we were told is 0.996 grams per milliliter. So moles cancel away, grams cancel away. So our answer would be in milliliter, and that would be 18.07 milliliter. Okay. Then we can use this information to calculate our work. Our pressure external is 1 atmosphere. Then we multiply this by final volume. Well, final volume is now this number, 18.07 milliliter, but the initial volume was given in units of liter, so we have to make sure they both have the same unit. So I'm going to change this to liter, and then minus the initial volume of 30.6 liter. You can see that when I do that, my final unit is going to be liter atmosphere, but my heat is given in units of kilojoules. So if I want to be able to add it later on, as I show you in this equation, then I'm going to have to convert my liter atmosphere to kilojoules, and we can do that, remember, by taking the two values of the gas constant and using that as our conversion factor. So 8.314 and 0.0821, and that would allow me to cancel my atmosphere, my liters, my mole Kelvin, so my final answer is going to be joules. Okay? And if you do that, you notice that you have a negative sign right here. Result of this operation is also going to be negative, so negative times negative is positive. Your answer is going to be positive 3.097 kilojoules. Heat is already given in kilojoules. So last thing I have to do is calculate delta E, which is W plus Q. The W is 3.097. Q, it says heat is released. Released means that it's a negative sign, so negative 40.66 kilojoules. So it ends up giving me 37.6 kilojoules. Okay? Now, the work quantity is positive, and that should make sense to you because what's going on here in this situation is compression, right? But remember that that same equation, which is the expansion work equation, it works both for expansion, which is volume going smaller to bigger, and compression, which is, like in this case, volume of a bigger quantity going to a smaller volume quantity.